Okay, so in this part, we're going to talk about simplifying radical expressions. Now, we've done that before, but with simpler kinds of problems. So, for example, if we look at this example here, and so we want to simplify this expression, so we have the square root of 100 times x to the 8th power. All right, now remember, when we're taking the square root or the cube root, whatever it may be, of a product, we can always rewrite it as the radical or the square root, cube root, fourth root, whatever it may be, of each factor. So in other words, the square root of 100 x to the 8th is the same thing as saying the square root of 100 times the square root of x to the 8th. And the square root of 100 is a perfect square, so the square root of 100 is 10 because 10 times 10 is 100. And then what we did here, one of the shortcuts you saw was that the exponent's 8, the index, if remember there's no number there, it's understood to be a 2, so we said 8 divided by 2 is 4. Now what we're using here is this rule, and this rule is going to be important when we look at something in a little while. So the rule says that you can always rewrite a radical expression. So let's say we had the nth root of a to the b power. You can always rewrite a radical expression and write it in exponential form. So you can write it, not exponential form, but a rational form. You can write it as a rational exponent. A rational exponent. So you can write this as a to the b divided by n. So the denominator is your index and your numerator is your exponent. Now remember, we also saw in a previous lesson that this right here, when you have a rational exponent and you can rewrite it as a radical, you can also rewrite this as the nth root of a all raised to the b power, and we saw that sometimes this was more useful. Okay, but so in this case, what you're using, although you're using a shortcut, 8 divided by 2 is 4, and also we're going to assume in this lesson that all the variables represent non-negative real numbers. So, so that means that you don't have to worry about using absolute value. Okay, so basically this right here, just to remind you, using this rule, so that's the same thing as saying x to the 8 divided by 2, which is x to the 4th power. So this is x to the 4th power. Okay? All right, now, so that was a review from a previous lesson. Now, what if we had this? So let's write this as number 1. So number 2, what if we had the square root of x to the 9th instead? So notice that when in a previous lesson, and all the problems were the same way, when we said 8 divided by 2, this index always divided into the exponent evenly. The remainder was 0. There wasn't any other remainder. But here, 9 divided by 2, 2 does not go into 9 evenly. There is a remainder. So how do we deal with this? Well, we're still going to use this idea right here to start with, and then you're going to notice there is a shortcut you can use just like we did this. There is a shortcut, but the intuition, remember when you use shortcuts, you tend to forget them at some point. But if you know the rule, if you understand the rule, then that rule kind of sticks with you, and you can get through some of these problems without any difficulty. All right, so we're going to use this rule here. So basically this right here means this. This means x to the 9 divided by 2. Okay? Now, the directions will say write your answer as in radical form if possible. All right, so so this is the same thing as saying x to the 4 1/2. All right, 4 1/2, because 9 divided by 2 is 4 1/2. Now remember this right here. Now you got to understand what I'm about to say. Okay, so you have to agree that this right here, x to the 4 1/2, is the same thing as saying x to the 4th power times x to the 1/2 power, because remember 4 1/2, let me go ahead and write that here. 4 1/2 is the same thing as saying 4 plus 1/2. So remember, a mixed number is the whole number part plus the fractional part. And so remember, when you multiply like bases using the product rule, so when you multiply like bases, you add exponents. So 4 plus 1/2 is 4.5. Now, see this right here is a whole number? Okay, now right here, if I cover this up right here, where you have this rational exponent, you want to go back and rewrite this as a radical. So when you write this as a radical, this right here, remember your denominator is your index and your numerator is your exponent. So this right here is the same thing as saying the square root of x to the first power, or just the square root of x. So that's just using this. So that's going backwards. And then you just rewrite the whole number exponent right here. So the square root of x to the 9th power is this right here. So it's x to the 4th times the square root of x. X to the 4th times the square root of x. All right. Now, the shortcut's this. Now, you got to understand what I'm about to say. Just like we did this. 2 goes into 8 4 times with no remainder. Okay, so see there's nothing else there. 2 goes into 8 4 times, no remainder. All right, now watch what happens here. 2 goes into 9 4 times, so you get x to the 4th, with a remainder of 1. So the remainder will be under the radical. So you're going to say the square root of x to the first power. 2 goes to the 9 4 times with a remainder 1. Okay? Now remember, that's a shortcut. There's really no understanding there as to, well, why is there a square root here? Well, the understanding is using this rule. Because this right here, when you have x to a fractional power rational exponent, you can always use this rule where you have a to a rational exponent. The denominator is your index and your numerator is your exponent. Okay, so number 3. Suppose you had the cube root of x to the 11th power. The cube root of x to the 11th power. Now, I am using cube root here for the most part, though. For the most part, in this lesson, we're only going to be dealing with square roots at some point. So, at some point, you're gonna see this just turning into just square root problems. All right, but right now we're going to use some other indices just to kind of talk about that shortcut. Okay. All right. So let's use the rule here. Let's use the rule here. Changing a radical. We're changing a radical to a rational exponent first. So this becomes x to the 11 divided by 3. Remember, you're just using this. So your index is your denominator, your exponent is your numerator. Now, rewriting this as a mixed number, that becomes x to the 3 and 2/3. X to the 3 and 2/3. And so, just like we did here, x to the 3 and 2/3, remember 3 and 2/3 means 3 plus 2/3. And so this becomes x to the 3rd power times x to the 2/3. Because when you multiply like bases, you add exponents. So this right here is this. And now this is a whole number part. Now what we got to do is rewrite the rational exponent part back as a radical. So you're gonna rewrite it back as a radical now. So this becomes x to the 3rd power. Remember, your denominator is your index times the cube root of x squared. And so there's your answer. So x to the 3rd power times the cube root of x squared. Now let's talk about the shortcut. So the shortcut's this. 3 goes in 11. That's what you're saying. 3 goes in 11 3 times. 3 times 3 is 9. And then 9 from 11 is 2 with remainder 2. So 3 goes in 11 3 times. So you can say x to the 3rd. X to the 3rd times the cube root of whatever the remainder is. So the remainder is 2. So you're going to say x squared. All right. Number 4. Number 4, suppose we had the 5th root of x to the 17th power. So we're going to talk about the using the rule first and then the shortcut. All right, so the rule says this. So I'm going to change this back to a rational exponent. So this becomes x to the 17 divided by 5. And so 17 divided by 5 is the mixed number 3 2/5. So that becomes x raised to the 3 2/5. And so now this becomes x to the third power times x to the 2/5 power. And so this is our whole number exponent. So got to rewrite this rational exponent though back as a radical. So this becomes x to the third power. And remember, the denominator is your index and your numerator is your exponent. So this becomes the 5th root of x squared. All right, now the shortcut, remember, said this. So we said 5 goes into 17 3 times. So you're going to say x to the third power, and the remainder is 2. So it'll be the 5th root, that's the 5th root of x squared. All right, so 5 goes into 17 3 times, and the remainder goes underneath the radical. The remainder was 2. All right, number 5. Number 5, suppose we had the 6th root of x to the 25th power. All right, now let's go ahead and use just shortcut. So the shortcut would be 6 into 25 is 4. So this is what you're saying, 6 into 25, 4 times 6 is 24, with the remainder 1. So you'd say that becomes, so 6 going to 25, 4 times, so x to the 4th power, times the 6th root, and you're going to say the remainder is 1, so you're going to say x to the 1st power. Number 6, now remember that's a shortcut. There's really no understanding there as to why it looks like this. The understanding is when we use our rules. So our rule was this. Oops, x to the 25th. So changing this radical to a rational exponent, I'm going to say x to the 25 divided by 6. And then 25 divided by 6 is this mixed number. It's x to the 4 1/6. And then I can rewrite x to the 4 1/6 as x to the 4th power times x to the 1/6 power. And now rewriting this rational exponent back to a radical, I get x to the 4th times the 6th root of x. All right, now remember, there's no understanding when you do a shortcut. That's why students tend to forget shortcuts for the most part. All right, now let's look at this. All right, so this is going to be number 7. Oops, sorry, going to be number 6. So we have the square root of x to the 8th, y to the 9th. So basically from this point on in this lesson, we're going to be dealing with square roots only. Okay, so the same idea. Now remember, for right now, you may want to use the fact that the square root of a product is the square root of each individual factor. So in other words, the square root of x to the 8th times the square root of y to the 9th. All right, and then let's just use the rules. So 2 goes into 8 4 times, no remainder. So that's just x to the 4th power. 2 goes into 9 4 times, so it'll be y to the 4th. And then there is a remainder, the remainder of 1. So it'll be the square root of y. And so there's your answer. Number 7. Suppose we had the square root of 16 x to the 12th, y to the 7th. All right, so remember our the square root of a product is the square root of each individual factor. So this right here, in your mind, you're saying the square root of 16 times the square root of x to the 12th. It is a good idea to write this like this, times the square root of y to the 7th. 16 is a perfect square, so 4 times 4 is 16, so that's 4. The index is 2, the exponent is 12, so 2 goes into 12 evenly, so that's 2 into 12 is 6. That's just 6 to the 6th power. 2 does not go into 7 evenly, so we are going to have a remainder other than 0. So 2 goes into 7 3 times, so that's y cubed, and then the remainder goes in the radical, times the square root. So 2 goes into 7 3 times, the remainder 1. So that's just y. There's your answer. And we tend to rewrite we put the radical in the end, so just remember the radical always goes in the end. Don't put the radical anywhere else. Mathematically, this is the way we write it. Now, technically, if you put it anywhere else, there's nothing wrong with it, but we tend mathematically to write the radical at the end. And we put the coefficient in front, and we tend to put the variables alphabetically. Okay? All right, 8. All right, 8, suppose we had the square root of 36, a to the 7th, b to the 9th. Square root of 36, a to the 7th, b to the 9th. Okay, so again, let's just rewrite this. The square root of a product is the square root of each individual factor. So the square root of 36 times the square root of a to the 7th times the square root of b to the 9th. All right, square root of 36. 36 is a perfect square. So the square root of 36 is 6. 2 goes to the 7 3 times, so that's a cubed, but I do have a remainder, so I'm going to have that square root here. And the square root of the 8 to the 7 is a cubed and remainder of 1. So this right here is this. b to the 9th, 2 goes to the 9 4 times with the remainder of 1. All right, now let's talk about how to rewrite this. Let's kind of review something. And we've been talking about this somewhat through this process. If I have the square root of 2 times the square root of 3, since the indices are the same, see the index is 2, when you multiply radicals and the indices are the same, you can write it as one radical. And so basically you're going to be multiplying the radicands together. So 2 times 3 is 6. So the square root of 2 times the square root of 3 is the square root of 6. Okay? So that means then this, the square root of a times the square root of b is the square root of ab. All right, so what you want to do here is this. So see how I have 2 radicals here, but in the others I just had 1 at some point. There was just 1 left, but here I have 2. So you want to take this, and you want to write it as one radical. So the square root of a times the square root of b, since the indexes are the same, indices are the same, you write it as 1. All right, so all the others though, you're going to put in front. So that's 6 a cubed b to the 4th times the square root of ab. All right, so that's how you write the answer. Don't leave the answer like this. This is how you write. Leave it like this, you're not going to get full credit because you need to rewrite the product of these 2 radicals as one radical. All right, number 9. Okay, number 9, suppose we had this. All right, suppose we had the square root of 16 x to the 13th power, y to the 15th power. All right, so the square root of 16 x to the 13th, y to the 15th. So again, it's a good idea to rewrite this as the square root of each individual factor. So I have the square root of 16 times the square root of x to the 13th power times the square root of y to the 15th. And so the square root of 16 is a perfect square, so the square root of 16 is 4. So we're going to, now here, we're going to say 2 goes into 13 6 times, so that's x to the 6th power, times the square root of x to the 1st, remainder 1. Here, 2 goes into 15 7 times, that's y to the 7th, times the square root of y to the 1st, remainder 1. All right, and then just like we just talked about, you're going to rewrite this as one radical. So we can get 4 x to the 6th, y to the 9th, times the square root of xy, just like this. So there's your answer. All right, number 10. Number 10. Number 10, suppose you had the square root of 25, a to the 6th, b. Square root of 25, a to the 6th, b. Okay. Now, so again, rewrite this as a product of each, as a square root of each individual factor. So the square root of 25, square root of a to the 6th, square root of b. 25 is a perfect square. Square root of 25 is 5. 2 goes in a 6th evenly, so there's the remainder 0. So 2 goes in a 6th 3 times, so I just get a to the 3rd power. No square root left like we had here, because the remainder is 0. Now, here the index, the exponent is smaller than the index, so we can't do anything to this. All right, so so it's just going to be the square root of b. So there's your answer. Okay, now notice that when we were doing all the problems and we took the square root of the coefficient right here, that coefficient, notice, were all of them were perfect squares. But that's not always the case. That is not always the case. So, for example, now remember we said perfect squares. So the square root of 16 is 4. 16 is a perfect square because 4 times 4 is 16. But if I look at this, 75 is not a perfect square. There is no whole number times itself that's 75. Okay? So, but what you want to do is simplify this. You want to simplify this radical. You're going to use the idea of, well, what is the largest perfect square that goes into 75? That's what you're going to use. What's the largest perfect square that goes into 75? So remember your perfect squares. The smallest perfect square is 1, so your perfect squares are 1, 4, 9, 16, 25, 36, 7 squared is 49, 8 squared. What I'm doing is I'm saying 1 squared is 1, 2 squared is 4, 3 squared is 9, 6 squared is 16. I'm sorry, 4 squared is 16, 5 squared is 25, and so on. 8 squared is 64, and so on. Okay? All right. So besides 1, what is the largest perfect square? You always use the largest. Always use the largest. It makes things a lot easier for you. So the largest perfect square that goes into 75 is 25. So that means this. I can rewrite this as the square root of 25 times 3. And just like we've been doing, I can write this as the square root of 25 times the square root of 3. And the square root of 25 is just 5. So the square root of 75 is 5 square root of 3. Now, that idea here is going to be important when we start looking at solving quadratic equations, because you're going to have to simplify the radicals that are involved in there. All right. Now, what if I had the square root of 32? So again, let's use the largest perfect square. So yes, 4 goes into 32, and we don't use 1 because 1 goes into every number. But 4 goes into 32, but that's not the largest. Use the largest. Makes things a lot easier for yourself. For example, so in this case, the largest is 16. So this is the square root of 16 times 2, which is the square root of 16 times the square root of 2, and the square root of 16 is 4, and you get 4 square root of 2. Now, if you had used 4, just want to show you what's going to happen now. You can use 4, but remember, you want to eventually get to this answer right here. So if you use 4, this is what you get. I get 4 times 8. 4 times 8 is 32, and 4 is a perfect square. So that becomes the square root of 4 times the square root of 8. And the square root of 4 is 2, and I get square root of 8. But then the question is this my final answer? The answer is no, because there's still a perfect square other than 1 that goes into 8, and in this case it's 4. So I can rewrite this. I can rewrite this as 2 times the square root of, remember 8 now it's 4 times 2. And I can rewrite the square root of 4 times 2 as the square root of 4 times the square root of 2. So I get this 2. The square root of 4 is 2. And then I get square root of 2. 2 times 2 is 4. So I get 4 square root of 2. All right, so notice the process you have to go through if you do not use the largest perfect square to begin with versus, well, what happens if I use the largest perfect square? You have fewer steps to deal with. All right. Now let's look at square root of 63. Okay, so what perfect square goes into 63? So you go through the process. Now, just remember that it could be that 1's the only perfect square that goes into the number. All right, so in this case, you would not be able to simplify it. But for 63, there is a perfect square other than 1 that goes into 63, and that is 9. So there's a square root of 9 times 7, and that becomes the square root of 9 times the square root of 7, and the square root of 9 is 3, and I'm left with the square root of 7. So there's your answer, 3 square root of 7. Square root of 54. 54, the largest perfect square that goes into 54 is 9 again. So that's 9 times 6. So that's the square root of 9 times the square root of 6. Square root of 9 is 3. So I get 3 square root of 6. All right. Okay, now let's look at number 10. Okay, number 10, suppose we had this. Suppose we had negative square root of 300 x to the 8th power, y to the 7th power, z to the 5th power. All right, so negative square root of 300 x to the 8th, y to the 7th, z to the 5th. All right, so again, let's just rewrite this individually. So that'll be negative square root of 300 times the square root of x to the 8th times the square root of y to the 7th times the square root of z to the 5th. That's what I have. All right, now let's deal with the square root of 300. Now 300 is not a perfect square, but there is a perfect square that goes into 300, and the largest perfect square that goes into 300 is 100. So that becomes the square root of 100 times 3. So the square root of 100 times the square root of 3, and the square root of 100 is 10, so that's 10 square root of 3. So that right here, this right here, is this. So that becomes negative 10 square root of 3. Now let's talk about the square root of 8, x to the 8. So 2 goes into 8 4 times, no remainder 0. So I get just x to the 4th. Here, 2 goes into 7 3 times, that's y to the 3rd. And I do have a remainder, so I'm going to have to say the square root of y to the 1st. Remainder 1. Here, 2 goes into 5 2 times, so I get z squared. And I do have a remainder of 1, so I'm going to say the square root of z. All right, now just like we talked a while ago, see all these square roots here, I can write as one square root. So it will be the square root of the product of the radicands. So in other words, the square root of 3 times the square root of y times the square root of z. Since the indices are the same, all I need to do is multiply the radicands. So it'll be the square root of 3yz. All right, so then all you got to do now is just rewrite these factors and put that in front of this radical. So I get negative 10 x to the 4th, y to the 3rd, z squared, times the square root of 3yz. And so there's your answer there. Okay? All right, so that's going to take care of this part of the lesson. We're going to do a few more problems like this in another lesson. But for now, you should be good with looking at the assignments dealing with this.